with the CPU.
Yeah, there you go. You know, but one thing I like to do is I like RC cars, like little radio control cars, right? And they get little electric ones. They get really, really hot as they run, and that heat makes them work inefficiently. It runs their batteries down. So what you can do is you can get electric fans that cool the motor down. One, it keeps things from being mechanically ruined, but it also makes them run more efficiently when they're cooler and they're wasting less.
A little waste car? I mean, a little waste car, a little.
Yeah, a little short course truck.
So what would you do? Like pop a little hole somewhere and like.
No, fan clips right onto the ECM. Little computer, little brain.
It's like an attachment?
Yeah, just clips right on.
You have to run the.
Because the ones that I have are came with the built-in capability for it.
Oh,
So it had it already wired in. Said in the correct way, the wiring harness is already there.
Yeah, my next question was, did you wire it together? Then?
No, it wired in. You can, but the wiring harness is already there, which is nice.
Quick
Okay.
question.
Yes.
The alternate power formula, I just looked at it and I'm like,
Ignore it. You'll never have to touch it. I specifically didn't talk about it. Good. I mean, if it's in a homework question, do the question, but ignore it entirely.
Next one.
All right, let's talk about waveforms, so electric current, okay? All right, so the reason why we have something called waveforms of electric current is because we want to be able to put on a graph, so a visual representation of what the electric circuits are doing, okay? And when you plot them on a graph, it creates these wavy graphs. So they create waveforms when you plot them on a graph. So let's describe those things. There are two basic types of electric current, okay? You can either have direct current, which is like your batteries in your car, or the batteries charging that are running your phones or my computer right now, okay? Little AA battery, right? Those all operate on direct current principles. Everything I've been describing with this parallel and series circuits and everything we've been describing, charge moving from one place to another, has all been implying direct current. Notice when we talked about current, electrons move from the place they came from through the circuit to the other end of the circuit, right? The whole time, the flow of electricity was in one direction. That's the important thing about direct current, is that electricity, which electrons are the electricity, so electricity always flows in one direction. The direction is away from the negative end and toward the positive end.
That's for DC, right?
Yeah.
Away from the positive to the negative?
Yeah. So you got your little battery here, right? A little positive side, a little negative side. You got a line that comes out of the battery and then goes up into a light bulb and then back to the other end of the battery, right? Okay. For that to work, right, for direct current to work, the electrons flow out of the negative end through the circuit, through the flashlight's bulb part, continue to flow until they get to the positive end. They are flowing from one end through the circuit to the other end. They never, and this is important with direct current, they never go the opposite way.
That's one way.
Just one way.
Because they would bump into each other. Right?
Well, they'd have to be, if they switch directions, something would have to be pushing them back the other direction, right?
And
They would.
and they repel each
They
other,
repel each
so they're not gonna.
They don't want to move the other direction
They don't want to.
because they're being repelled from that direction. Yeah, exactly. The exact other way to think about it, which is equivalent and the same, is they're being pulled towards the other direction, right? They're being repelled from one direction and pulled towards the other, so they only move in one direction, toward the positive charge, away from the negative charge. Said in the way we use it, talk about an X-ray, toward the anode and away from the cathode. The name for the positive end of any circuit or battery is the anode. The name for the negative end is cathode. In an X-ray tube, we talk about cathodes and anodes. We don't say negative and positive. And in your battery, your negative side, the flat side's the cathode, nipple side's the anode.
So AC would you say is mostly all motor products?
Yes, every AC motor, I even said it, every motor is an AC motor, yeah, yep. Okay, so then, okay, so here's the problem, right? What have you learned about wire, conducting wire so far? So you're right, that's the thing I'm getting at, but hang on to that for just a second, because that's exactly the answer I wanted, but I was hoping maybe for a slightly different thing first. So, no, she's got the right answer though. So wire has, conducting wire, right, allows electrons to flow, right, but has some resistance to it. That's what Abby just told us, right? A wire offers resistance, okay? You learned that the wire offers resistance, and the longer the wire is, the more resistance there is, right? The thinner the wire is, the more resistance there is, okay? But for right now, just consider length of the wire, okay? So I haven't talked about alternating current yet, but let me explain why DC current works for some things and doesn't work for others, okay? DC current works for my for charging my phone, okay? Let me rephrase that. Works for discharging my phone. My phone is charged right now. It's running on DC current, okay? It works because the battery and my phone are very close together, okay? The battery's inside my phone, okay? Very short distance to travel. Not a lot of resistance in the wires, right? However, your home, where does your home get power from? Assuming you don't have, even if you do have solar, but assuming you don't have solar, where does your home get power from? Inside your home you get power from the outlets, but how does the power get to your home? Where's it coming from? The power lines, which leads to away from your house and toward the power plants, right? Okay. And is your power plant next door? No. Do you even know where your power plant is? No. So said in another way, your power plant is a long ways away from your house, right? But nevertheless, the power originated somewhere way far away and has made it all the way to your house, right? Okay, so let me describe direct current in a little bit more depth here. Okay. There you go. So hang on. So remember this. Remember Ohm's law. As we talk about this, remember Ohm's law. Okay. All right. So you've got a power plant. Okay. And it takes power along power lines to your home. Right. Power lines connected to the ground. Let's say. Right. So you got power flowing across and along the power lines toward your home. Let's say your home's right here, okay? Little happy little house, couple of windows, okay? Happy little house and a door. All right, good. The power line connects to your home, okay? If you are right next door to the power plant, okay? With direct current, the power plant pushes power to you, okay? With direct current, power plant. You're right next door, power plant pushes power to you, no problem, right? But as you get further and further and further away from the power plant, how is the power plant sending the power to you? Like, what's it sending it? It's not sending it through the air, right?
Wires.
Through wire, you're going to something, but the wires, right? It's sending it through wires, right? We know wires have resistance, okay? So if your power plant was operating on direct current, only sending power in one direction, then it would have to push the power along these power lines. And if your house is, here, right, you're going to receive some power at some voltage, at some amperage, and some resistance, right? If your house is down here, you've got more resistance, okay, because of the longer wire, okay? So the houses that are far away, the resistance number is bigger, okay? Resistance goes up.
So the houses that are closer, they have less resistance.
Yes. So, to be clear, your power plants are not DC. They don't use direct current. I'm trying to explain right now why they can't, okay? So your power plants, if your power plant was direct current, the first house would have some resistance. So remember, what's the voltage that our houses get? 110, right? They also get 220, but ignore that for right now. Houses get 110 volts, right? So the voltage number is fixed, okay? If the voltage number is fixed, this house gets 110 volts, okay? This house also gets 110 volts, right? But what's the difference between that house and that house? This house is closer with less resistance. That house is further away with more resistance. What's the relationship between intensity and resistance if the voltage is fixed? If resistance goes up, what has to happen to that intensity number? Has to go down, right? So what's that mean for the house at the end?
So
It's not gonna have that much power.
There you go. The house at the end gets less amperage, less current, not as much power. Because remember, power is voltage and amperage, right? The voltage is fixed, but the amperage is now going down. So the house at the end gets less amperage, and because of that, it has less power, okay? And there's not just two houses, right? There's a bunch of houses between you and the power plant. So each one of them, further and further away, would get less and less power, okay? Direct current was the first type of power plants invented. Thomas Edison invented them. What do you know?
Edison invented them, and then Tesla invented AC,
Yeah.
which was better and more safe.
Yeah.
But then Edison ran a smear campaign
Yeah.
where he electrocuted a bunch of elephants to show everyone how dangerous it
Yeah.
was, even though he was totally unethical in doing so. And then Tesla
So-
died a very sad death.
Tesla died a very sad death. So Edison said, so Edison goes, and Edison was no dummy, okay? You guys know Thomas Edison was no dummy because we still talk about him today, okay? So he was no dummy. He knew this. He knew Ohm's law, okay? And he knew that the house far away, he came up with DC, he wanted to build his DC power plants. And he's like, well, I know what's going to happen. This exactly as I described is going to happen, right? So Edison goes, all right, I got a fix for that, okay? Let's put a power plant here, and let's power all the homes on this block with that power plant, okay? And then down here, let's just build another power plant, right? Let's build another power plant down here, another DC power plant close to this block of homes,
So each
okay?
neighborhood gets.
Each
a
neighborhood
power
would get
plant?
their own power plant.
That's why they go out of power in certain sections.
Well, that's because there's a grid set up. Remember, this is not the way our power plants are set up.
So we
okay?
run on AC?
We do run on AC. So yes, you guys are doing great. So Edison said, let me put DC power plants every block, okay? And he did it in a small area, and the problem was exactly as you might imagine. You know power plants produce waste, right? So now you've got one every couple of blocks, right? Lots more waste, and it took so much energy to run these power plants, okay? It was hugely inefficient because of this resistance thing of the longer lines adding more resistance. So this was a problem, okay? And even in those short couple of blocks, the homes that were furthest away wouldn't get as much power as the homes that were close by, okay? So now instead of that, Nikola Tesla comes along and says, well, I've got a better way to do this, right? And they knew about alternating current. Tesla just made it work right, okay? So alternating current says,
And they work
okay,
together.
and what?
They work together.
Yes, and they work together, yes. That's what it is. Okay, that's right.
Do I just turn these in?
Hang on to it. I was going to initial them, but just hang on to it. Okay, so alternating current. Instead of sending the electrons, the electricity in only one direction and having to deal with all this resistance problems, right? Let's shake the whole thing back and forth. Let's move the, oh, that's what's happening. Let's move the electrons back and forth, right? That way at no time do you have to move them all in one direction, and you're not relying on, you're not beholden to the resistance of this long wire, okay? The resistance part of it is not important now, okay? The house far away in alternating current is going to receive the same power as the house close by with an alternating current. So once you switch to AC, now you don't need a power plant every couple of blocks. You need one power plant that can send power out very far away. Okay, so shaking the electricity back and forth in the lines allowed them to send power over very long distances because the resistance became negligible at that point. Okay, the resistance didn't increase the further away you are. Okay. All of every AC motor, every motor-driven device uses alternating current, okay? We use both in the X-ray machine, and in different spots. So when we talk about the X-ray tube, we'll get to that. But let's talk about a couple more things. So, oh, hang on. Okay, let's list a couple more things, hopefully make this make a little more sense, then we'll start showing the graphic representation of this. So, current, all right? Remember that the source, the battery that you're using, the power plant, wherever the source of electricity is, remember that's not the source of the electrons. What's the source? It's the source of the power, the push, right? What of the three things of the power source, of the conductor, and the device? What is the source of electrons? Where are they coming from? Not the source. It's the conductor. Remember the electrons, a conductor is something that has loosely bound electrons, right? So the conducting wire is the source of the electrons, okay? So for analogy purposes, your wire is kind of like having a tube full of ping pong balls, little, in this case, little green balls, okay? So your wire is kind of like that, kind of like a tube full of ping pong balls, okay? And with direct current, you're standing over here with your battery, right? You have all your negative charge on this side, right? And when you close the circuit and turn the device on, the tube is full. One ping pong ball is shoved into the tube, which is full, causing a ping pong ball to fall out the other end, right? If these were electrons, one electron hops from one atom to the next, away from the source, right? That atom is full of electrons, so it has to push an electron over to here, which has to push one over to here. And this, remember we talked about like the leapfrogging of electrons across through the conductor. Well, the conductor is full of electrons. As soon as you push one electron this way, one at the other end, no matter how far away the other end is, has to be moved. Okay, they all have to move over.
Like that one thing where it has like balls and you just pull them.
Newton's cradle? Yeah, Newton's cradle. It's like that. Yeah. And the idea that the energy is transferred, right? So that's what has to happen, right? With DC current, the electrons move in one direction, okay, and are pushed from the negative end toward the positive end. And as soon as you like turn your switch to your flashlight, it lights up immediately, right? Okay, it's because your flashlight's light bulb is already full of electrons because it's a conductor. The conducting wires going from the battery to the light bulb are conducting wires, so they are full of electrons. So as soon as you turn that source on, that source pushes on those electrons and gets them all moving through the circuit together. Okay. Here's what's interesting. If you were to track, can't do this, but in principle, if you were to track a single electron, okay, and you turn your DC circuit on, and then you came back an hour later, and you'd want to know where is that electron, right? You name it, you give it a name, you give it a nice little button-up shirt and a tie, and you say, that's the electron I'm going to follow, right? And it come back an hour later, it's not going to be at the other end of the circuit. It's going to be about an inch away, okay? It will have moved only about an inch in an hour. But remember, the electrons are very, very small. So 1 inch of distance for an electron is a long ways, okay? So it is not the case that the electrons come out of the battery and move through the entire circuit to the other end of the battery, okay? Kind of like we've been using as an analogy. It is true that the conducting wire is full of electrons, and as soon as you start pushing on one end, they all start to shift over. They all start to move, okay?
When you turn off the light, on and off the light, like say you turn it off, you just stop and then when you turn it off.
Yeah, the electrons just stop. Yeah, and you're not going to run out. You're not running out of electrons because as you're pushing them through the wire, more are coming into the wire from the source. So it is sort of true that the source is a source of electrons. But yeah, as soon as you turn it off, electrons stop. Yep. And they stop moving, and then you turn it back on, and they begin to move again. Sorry, my phone is blowing up. Just want to make sure it's not recording. Because what?
Because they become stable.
Because there's no potential difference. Yeah, they're stable. Yeah, there's no energy applied to them.
Okay, so does that process deteriorate the source material?
Not in the way you think. Not in that way. It's not like you're going to run out of electrons and the material falls apart.
Right, because they're being replenished.
But what does, you'll notice that wires get brittle over time, right? Part of that is like oxidation, right? Oxygen adhering, but part of that is the heating up and cooling down. Remember we talked about magnetic domains and all the atoms lining up with each other, right? Well, when you heat something up, you jiggle around the atoms, right? You change their orientation, and over and over and over as you do that and do that and do that, it weakens the material. So the material gets weaker over time and more if you measure the resistance in your household wires, right, it goes up over time, okay? This is because the materials become less and less conductive over time. So eventually they gotta be replaced, or usually it's when your house is torn down and rebuilt and they replace it then.
You know, the outlet that catches on fire.
Yeah,
And that's why.
that's part of the why, you know, insulation breaks down and, yeah, but yes, yeah. So the conductor does lose integrity, but not because it's losing electrons, it's because the internal structure of the wire is changed so many times, right? Reason why engines crack, right? It's because you heat them up and cool them down so many times, they expand, contract, and it just weakens the material. It's like bending a wire repeatedly, like it's gonna crack eventually. Like welding, exactly. Good, okay. Good. All right, we're making progress, I think. That's a good thing. Okay, so DC current, electricity moving in only one direction. We graph it like this, okay? So, hopefully you guys have seen graphs before that use the X and Y axis, okay? So these are two-dimensional graphs, okay? There is a vertical axis, the Y-axis, and then there's the X-axis, the horizontal axis. I don't even care about X and Y right now, but you could plot these on, you guys remember, I don't know if you remember the Cartesian graphs in like math class, right? It's just that there's a center point on the graph and you got a vertical axis and a horizontal axis and you can plot things on it, okay? Anyways, that's not even that important. It's just important that you understand what the graph is telling you, okay? So the vertical axis on the graph tells you charge, right? So here at zero charge, okay? 0 voltage, nothing's happening, okay? If one point on the graph is above the 0 point, okay, then it is moving toward the positive charge, okay? So at this time, right where I put this mark, all the electrons are moving toward the positive charge, okay? Notice how on this graph, none of the wave form on the graph, this wave on the graph, right? None of that wave, doesn't look super wavy when it's DC, but none of that, it's still a wave, none of that wave is moving toward the negative. It's all above the baseline. So this graph is telling us that electricity at time equals 0, okay, is not doing anything. Time equals 0, the time hasn't started, we haven't turned it on yet, okay, t equals 0. 0 time, and the device turned off, nothing's happening, so we're here, okay? If we just left the device turned off, and we just started a clock, right, so I turn the lights off in the room, right, and I start a clock, right, the graph of this room's light use right now would start at 0, and then as time went on, it would just be a flat line staying at 0, okay? Nothing moving, no electricity moving, okay? As soon as I turn the lights on, we get a spike toward the positive, okay? And if it's a DC, if our building's running on a battery instead of the power lines, it would continue above the baseline until I turned it off, and it would go back to 0, okay? Which is what's shown here on this graph. So this is telling you over time, so time equals 0 to the end of time, to the end when we stop counting this, we're off. We turn the device on, it stayed on, let's say it's a flashlight, so it stayed producing light, and then right here, we turned it off, okay? And when we turn it off, all those electrons which were moving toward the positive charge, they were, remember the battery, right? The electrons were moving from this end toward that end the whole time. Okay, so the whole time the electrons were moving toward the positive end of the battery. This vertical axis indicates direction. Above the baseline toward positive, you're moving toward the positive end of the battery, let's say. And as long as the device is left on, you get this flat line showing you that the device is on, okay? The height of this wave tells you the voltage. If this wave were, so this is this point right here where the wave is the height, the max height of the wave, right? The amplitude of the wave, that's at 3 volts, okay? If this wave were exactly twice as tall, then it'd be at like 6 volts, okay? The height of the wave tells you how much pressure, how much push there is through the circuit. How long along the horizontal axis the wave is tells you how long the thing was turned on for, okay? We haven't actually put a time in here because it's not important. The time is not important. It's just important that you understand what the graph is telling you. A graph like that is telling you that you turned a device on. That's the point at which it lit up the brightest. The electrons have to accelerate toward the positive end. They stay moving toward the positive end, and then as soon as you turn it off, the electrons decelerate back to zero velocity. Okay, so this is the waveform of DC. So the waveform of the graph shows a period of acceleration. That's this little up swoosh, okay? That's when the switch is turned on, followed by steady pressure as the device is running, okay? Followed by deceleration of those of the electrons in the circuit as the device is turned off, okay? So it's turned on here, and it's turned off right there, okay? And once it's turned off, all the electrons decelerate, nothing's moving, everything's stationary, sitting still, okay?
So you had a graph where you noticed the light switch.
Oh my god, yeah.
It'll be like,
They go all over the place, right? Alright, good. So, that's DC. So if you had something that looked like that, right?
That's what I was gonna ask you, what happened if,
Yeah, so that's telling you it's flowing the opposite direction. Electrons are being pushed toward the negative. So because of something in the charge, the electrons are being drawn the other direction. So an upside down waveform like that for DC is telling you the electrons are just moving the other way. Okay, they're going, in this case, they're being pushed toward the negative side. Okay, the voltage was negative 3 volts instead of positive 3 volts. Not important, not that important. They're only showing you the negative right here because in a second here you're going to look at alternating current, AC current, and that has positive and negative pulses inherent, okay? Again, the moral of the story is, you guys all right? In the back? Okay, good. The moral of the story is the vertical axis indicates direction, okay? Toward positive or toward negative, okay? The horizontal axis tells you how much time has elapsed. Let's look at AC current now. So here's an interesting thing. Your X-ray tube, in order to produce X-rays, the actual X-ray tube part of it, the thing that does the X-ray making, the light bulb type part of the tube, that has to use direct current, okay? But your X-ray machines plug into the wall and have to access alternating current. So we're given alternating current for free, right? We get it from the wall, right? And then we'll have to do something to the alternating current to make it look like DC current, okay? Because our X-ray tube needs DC current. We'll explain why later. I'm not going to get to that part today. So AC electricity. The waveform when plotted, ignore this really, if you weren't here for physics, just ignore that, okay? So the point is about AC is that the electricity takes turns alternating direction toward positive, toward negative, toward positive, toward negative, back and forth, right? If you had this, if this is your AC power plant, right? The electrons would move toward the positive direction for some period of time, and then they would be switched around and moved back the other direction, and they shift back and forth in the wire, back and forth, okay? And it does it in a specific amount of time, okay? So I will get to that in just a second. Okay, good. All right. So what we'll say is that one pulse towards the positive, this pulse, followed by one pulse towards the negative, completes one cycle. Okay? We call one cycle the unit that we'll use is a unit called the Hertz, H-E-R-T-Z. Okay? If something happened at 1 cycle per second, then it's happening at a rate of 1 hertz. Okay? I like goofy analogies because they help take us out of the technical stuff here. So if I come up to one of you guys, or if I'm here at the front of the room and I throw a tennis ball at you, okay, it hits you, right? And another, 1 second later, you're hit with another tennis ball that I threw at you. So every second I hit you with a tennis ball, okay? Well, what's the frequency that you're being hit with the tennis ball?
Every minute.
It hurts, right? 1 tennis ball per second, right? And it's a cycle. I throw a tennis ball, I throw another one again, right? And I get hit by 1 per second. You're being struck by the tennis ball at a rate of 1 hertz. 1 tennis ball per second. Yeah, go ahead.
I was going to say, like, the last time you explained this, you talked about, like, the ocean wave.
Yeah, I was going to use that one too. So I love the ocean analogy because it's literally waves, right? So go to the ocean, right? Stand in the water, however deep you want to stand, however deep you feel brave enough to stand, right? And then as a wave hits you, that's one wave, right? The next wave, however much time it took for the next wave to hit you, right? That is the time for the whole cycle, okay? Between the amount of time between waves. Imagine that you're standing in the ocean, knee deep or whatever, and you get hit by 1 wave, and then you get hit by a second wave 1 second later, okay? Then you're being hit by waves at a rate of 1 hertz, okay? So now you stand in the ocean, 1 wave per second, and some magic happens out there in the ocean. Now the waves increase in their frequency, okay? You're now hit by 2 waves per second, okay? The frequency is 2 hertz, right? Now ramp it up. You're now hit by 60 waves per second, okay? 60 waves from the ocean are hitting you every second, okay? You should probably get out of the water, right? Okay, but importantly, 60 waves are hitting you every second, okay? You're being hit at a rate of 60 hertz, okay? What's the difference that you experience, literally in the ocean, you're standing in the ocean, picturing it in this thought experiment, what's your experience, how is your experience different from 1 wave per second to 60 waves per second? Each wave does something to you, right? Each wave might move you around a little bit, right? And 2 waves moves you around a little bit more. 2 waves per second get shifted around a little bit more. But 60 waves per second is going to knock you around real hard, right? Yeah. Notice that each wave, if spread out over long periods of time, 1 wave an hour, not a big deal. 1 wave a second, probably not a big deal, right? But you put 60 waves that close together, right, in 1 second's time, each wave carries energy, right? And if you pack more waves into a shorter amount of time, that's more energy over a shorter amount of time, or more power, right? The waves are putting more power into you. They're going to knock you down, okay? That's why I said you should probably get out of the water at that point, right? Something's wrong if 60 waves per second are striking you. So that's how AC current works, okay? Not exactly like the waves in the ocean, but it's a good way to picture it, okay? AC current sends the electricity this way, and then back that way, and this way, and then back that way, and it shimmies it back and forth in the wire, okay? Pushing it away from and toward the power plant, shifting back and forth. Toward the house would be toward the positive end, right? Back toward the power plant is the negative pulse. 1 positive pulse followed by 1 negative pulse, 1 shift this way followed by 1 shift that way is 1 cycle, okay? Our homes here in the United States get power, homes and businesses get power at 60 hertz, 60 cycles per second, okay? If you go over to Europe, I've never traveled overseas, but I know that when you do, you have to buy new little charger bricks, right, for like your phone or computer or whatever, because their outlets are different. They look different than ours for good reason, because their outlets produce electricity at a rate of 50 hertz. Okay, they just use a different frequency, so our devices would not be compatible with theirs. Okay, so you have to use different plugs. All right. So the next thing to go, the step up from this is we need to know that if something happens at 60 cycles per second, then a single cycle only lasts for 1/60th of a second. Okay? How many pulses did it take to make 1 cycle? one cycle? Two pulses, right? One pulse going toward the positive and another pulse going back toward the negative. That's one cycle. That whole cycle of two pulses, one cycle, took 1/60th of a second. Well, what's half of 1/60th? 1/120th. So please don't say 1/30th. It's 1/120th, okay? So each pulse lasts 1/120th of a second. You can real easily plug into your phone 1 divided by 120 and it'll give you that answer, okay? Ignore that right now. I don't need you to worry about that. What's important here is these nice little fractions. They're easy to remember. Okay, so in our household AC current, it's an alternating waveform. Each pulse rises to a full pressure of 110 volts. But what you should notice is, so a couple things. The distance between crests of a wave, between common points on any wave, you can measure the distance from here to here, right? This distance and that distance will be the same, so it doesn't matter which part of the wave I measure as long as I measure a common part on the wave, but it's common to take the crest of the wave, okay? The distance from one crest of that wave to the next is called the wavelength, okay? Wavelength. If you remember wavelength from light, don't confuse this with the way it's the same idea, but we're talking about electricity. Okay, so wavelength. If the frequency were higher, then the wavelength would be shorter. More waves per second, right? Higher frequency equals more waves per second. So over 1 second's time, you'd have to squish more waves into that space, okay? So this distance is called the wavelength. Waves, these are called sine waves. All waves that have an up and down to them, sine waves. Sinusoidal is what it stands for. But all waves like this, all alternating waves, have a wavelength. They have a amplitude, which is the maximum height or depth of the wave. Okay, how high the wave gets. Okay, notice that the wave is not. Notice the wave is not like that. It's not a block. Okay. Remember how, I don't know if you guys heard Javier talking about his inverter that he has at home. One has a sine wave, the other has a blocky wave, right? He was talking about the different wave shapes. This is what he was talking about, okay? If the wave looked like a block, that would say that as soon as you turned it on, it went to full power, maintained full power for that whole pulse, and then immediately went to zero, okay? However, that's not the case. As soon as you turn it on, those electrons have to accelerate towards full pressure. And because of that, you only get a short period of time where you're actually at 110 volts, okay? You reach a pressure of 110 volts, and then immediately they slow down so that they can go back to zero movement and move back the other direction to a maximum negative pressure of negative 110 volts. We only get full pressure or push at the crests of the waves, okay? The rest of the time, the electrons are either accelerating or decelerating, okay? They're being sent that way and then sent back that way, okay? Somewhere in the sending direction, right, halfway through being sent in that direction, halfway through being sent toward positive, they're at their maximum speed. The rest of the time they're slowing down, right? It's analogous to if I wanted you to run as fast as you could toward a wall, right? But don't hurt yourself, okay? What would you do? You would start at a spot, right? You would begin to sprint as fast as you could towards the wall, right? But you don't want to hurt yourself, yeah? So what do? You sprint as fast as you can, and then before you hit the wall, what do you have to do? Stop, right? You have to slow down. You don't immediately stop, right? And you don't immediately accelerate to your full speed. Let's say you can run 15 miles an hour, right? You had to start not moving, right? You're an electron, you had to start not moving. Then you had to accelerate in one direction. At some point during your acceleration, you went from 0 to your maximum speed, right? And then before you hit that wall, you had to start putting on the brakes and slowing down, okay? That's analogous to the electrons accelerating one direction, and before they hit the wall, they have to slow down to move back the other direction, okay? You have to accelerate and decelerate If we didn't have to accelerate and decelerate, the waveform would look just like a block. Okay, but it looks like a wave like this because of the acceleration, deceleration. Okay, good. So, one full cycle, starting at 0, moving through one entire positive pulse and one entire negative pulse and ending back at 0 gives us one full cycle, one full wave, 1/60th of a second. Half of that distance, right? One pulse width of distance is 1/120th of 1 second. Yeah.
Can you briefly explain why it goes down into the negatives again?
It's direction.
Okay, direction.
Yeah, so this is, so the positive direction, consider the in the power plant, power line, house analogy that I was using, consider the house to be the positive side, and consider the power plant to be the negative, okay?
Okay.
So then positive and negative is just direction, right? During the positive pulse, electrons are being pushed away from the power plant, okay? On the positive pulse, they're being pushed away from the power plant, and on the negative pulse, they're being sent back toward the power plant. It's direction, back and forth, okay? So that's what the negative means in this case. It doesn't mean, usually when we think negative, it means like, if I told you I had negative 5 apples, it would mean that I owed somebody 5 apples, right? That's not what we're saying here. It's direction, okay? That's why I said don't worry so much about the negative and positive. In this case, we're going to treat them like directions. Okay? This is really what it is, okay? It's direction away from or toward the positive or negative charge, okay? Negative doesn't mean you don't, negative does not mean you have less than 0 of something in this case, yeah, good. But I think that's what we're used to in math, okay. So again, why is this important? And I'm getting to the end of this here, I won't go too, let me just really quickly see how much more I've got. Yeah. Yeah, let's see. I'm going to give a couple more notes here. I don't think I'm going to get that much further, but let's just bear with me, please. All right. So why is this important, right? Well, it's important because you have an X-ray machine that has to operate. Your X-ray machine has to get power somehow. We don't run our X-ray machines on batteries unless we have a mobile X-ray machine, in which we don't even talk about those, okay? But some X-ray machines do run on batteries like your phones do. Ignore that. We have to plug our X-ray machines into the wall, okay? Which means we're going to get alternating current from the wall, but we don't want alternating current, okay? On top of that, we have a current type that we don't want. We're just stuck with it, okay? We want DC current. It's the best kind for operating the X-ray equipment. We get AC. So we have to do a couple of things. We have to convert alternating current to direct current. That's called rectification. We'll deal with that probably next class. And we have to take the voltage that we get from the wall and increase it from 110 or 220 volts all the way to 50 to 120,000 volts. Okay, so we have to make high voltage from a low voltage plug. Okay, and by now you should be okay with that because you learned Ohm's law and you learned voltage can be manipulated by manipulating amperage and resistance. Okay, so it's something I will get to talk about next time. But anyways, the point is you need something called a generator to make enough power to make the X-rays. Okay, remember power is amperage and voltage, right? You need enough power to produce X-rays. Okay, so the AC waveform is typical of electric generators. These generators make the electricity for us to use, and it's got to get converted from AC to DC at some point. We're not talking about the conversion yet. We're just talking about the fact that you can make alternating current with a generator. Okay, so our wall gets power, and we get power from the wall, and we can access it to make more energetic AC current. So some lessons from the previous class, or if you weren't here, the videos you watched on my channel. There were some things done in the mid 1800s that showed that a moving magnetic field, and you know magnets have a magnetic field around them, right? A moving magnetic field can move electrons in a nearby wire. Said in another way, a moving magnetic field can create electricity, okay? And it should be no surprise because we've learned by now that atoms have their own electric charge. Atoms are always in some version of motion, and atoms all have a magnetic field around them, okay? The magnetic fields, so two magnets, right? An atom is like a little magnet, and a bar is like a bar magnet is a magnet, right? Well, magnets can repel or attract towards each other, right? So if you bring a magnet near a conducting wire, and you move the magnet one direction along the wire and then back the other direction, you are literally shifting the electrons in that wire back and forth, okay? Well, what's that sound a lot like? That sounds a lot like electricity, right? Moving electrons is electricity, okay? So we can take advantage of, to start off with, explaining it by talking about magnets, okay? So here we go. Imagine that you had a magnet, a permanent magnet, so not an electromagnet for right now, okay? So it's literally your refrigerator magnet, okay? But it's a bar shape. Doesn't matter that it's a bar, but let's call it a bar shape. That magnet's going to have a north pole and a south pole, right? We learned that last time. And you probably also learned that it doesn't not important for this, but you probably also learned that if you broke that bar magnet in half, you wouldn't have a south pole magnet and a north pole magnet. You just have two smaller magnets now, each with a north and south pole, right? Magnets are always dipolar. Anyways, there is a north pole into that magnet and a south pole into that magnet, okay? For this analogy, let's say that when we point the north pole of that magnet toward the bar, so there's the bar running like that, the magnet pointing like that, the magnet can spin and that metal bar or wire is stationary, let's say. As we rotate that magnet like that past that bar, it's going to drag the electrons in that bar one direction, okay? And as it rotates to the south pole facing up, those electrons will be repelled the other direction. So you get this pull and push as the magnet rotates north pole, south pole, over and over again, okay? If that magnet did that and made one full turn in 1/60th of a second, it would make 60 full spins in 1 second, or 60 cycles in 1 second, and we could graph it just like that. As the north pole gets to the pointing towards the bar, begins to pull those electrons toward the positive end, toward, let's say that's positive, that's negative, so it begins to pull the electrons toward that way, right? And as the magnet flips the other way, the electrons are repelled the other direction, okay? And back and forth, back and forth, back and forth, because the magnet can affect the electrons. The magnet has a magnetic field. Electrons are electrically charged, and they have a magnetic field. Remember, if you don't remember from last time, it's because electrons have something called spin. The spin was the spinning of the electron. And that spin creates a magnetic field. So the electrons in matter are like little magnets. And magnets can interact with each other. Okay, they can either repel or attract, okay? So the big magnet is pushing and pulling around all of these very small magnets, okay? All of these very small magnets, if they're moved, is what we call electric current, okay? The moving electrons is what we call electric current. So each position can be shown like this. With the bar horizontal, there is now an equal amount of push and pull. Said it another way, nothing's happening, okay? If the bar is horizontal, nothing's happening. At point A here, nothing is happening, the bar is horizontal, okay? As the bar spins, it begins to drag the electrons in one direction. That's shown as the crest of the positive pulse. When the magnet it's pointing straight up towards the bar, it's closest to the bar at that point, right? So it has the most push or pull, and that's the crest of the wave. And as that magnet continues to rotate, shown here, back to horizontal, we're back to no movement at all, okay? And now we go to the south pole facing up. Well, the south pole of the magnet is going to pull the electrons the exact opposite direction than the north pole did, okay? So in that case, D here, you get a negative pulse when the south pole is facing toward the wire, okay? And then you just repeat. You just keep spinning that magnet, right? Magnet's got a south pole and north pole, and every time you complete one cycle, one full spin of the magnet, you get one positive pulse followed by one negative pulse. And if you can spin that magnet around 50 times a second, then you get a frequency of 50 hertz. Spin it 60 times a second, you get a frequency of 60 hertz, which is what we'll use here. Okay? So this is, yeah, go ahead, please.
So, I'm a little distracted by the image. The image is one magnet.
Yes.
It's just
Over
showing a
time.
different revolution.
Yes. So, yeah, to be clear, this is
not
just,
four different magnets.
no, this is one magnet shown at different points in time, right? Remember, this axis is time. Okay. So yes, very important. So this magnet is just on a bar, on a rod spinning. Okay. And the wire in this analogy is placed right above the magnet. Okay. So when the magnet points towards it, the magnet can drag the electrons one direction. When the opposite end of the magnet is pointing up, the south pole's up, the electrons are pushed the other direction. So you get this backwards push and pull from the magnet rotating. Okay. Okay, so a magnet has a magnetic field, okay? The magnet doesn't have to do anything special to have the magnetic field except for in its structure, all of its atoms are all lined up in one direction, okay? That's why it's a useful magnet, right? We talked last time about like dropping the magnetized screwdriver and having it lose its magnetic properties. Anyways, you've got a magnet, it can do that, you're happy, you can make electricity with that. So in principle, if you can have a wire and you've got a magnet nearby, you can induce current in the wire by rotating the magnet. You don't go home and start spinning a magnet around, you're not going to make it happen. But it does. In principle, this is what does happen, okay? So remember that a magnet has a magnetic field, but what else produces, how can you produce it? Is there anything we can do with electricity to produce a magnetic field? Yeah, run the electricity through a wire, right? You learned in a previous lecture that moving electric charges, electrons are electrically charged, so a moving electric charge generates its own magnetic field, okay? So if we instead of the magnet, had some version of an electric field moving, we can generate our own magnetic field, okay? It's probably not, I'm not going to get into that too deeply today, but that's the idea here. So let me give you my last couple of notes for the day, and we'll probably call it good. Yeah, I know. All right. Good. Okay, so some notes here, final finishing notes for today, okay? Technically speaking, the electrons are at rest, they are sped in one direction, they stop, and then they are sped in the other direction. They are pushed and pulled in back and forth opposite directions. So technically they stop directions, but it's happening so fast that during the time that the device is turned on, during the time you're accessing that AC power, it's as if the electric charge, the electricity never stops moving. Do you notice your lights flickering on and off 60 times per second? No, right? No, you don't notice that, right? They do. They are flickering on and off 60 times per second, okay?
When they get bad,
Have you ever had, like with your digital cameras or anything, interference so that you can almost see the flickering on and off? It's because your camera's frequency of the frame frequency is like matching up in a weird way with the frequency of the lights being emitted. So it is true that this is happening 60 times a second. The electrons are being shifted back and forth, and there is a teensy-tiny fraction of a second where no light's being emitted, okay? And every one of those pulses, when the pulse goes back to 0 voltage, no light's being emitted for that short period of time. But it's such a short period of time that you can't tell, okay? So it looks continuous to us, even though it's not. It really is pulse, 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 pulse like that, 60 times per second. You just can't see it, okay? AC electricity never stops changing its speed. It's always accelerating or decelerating for our purposes. So yeah, not only does it turn on and off, the lights actually go dim to bright to dim to bright to dim to bright, back and forth, again, happening too fast for our eye to detect. In our X-ray room, the AC electricity that we access is good for running a small AC motor that spins the anode. What do you guys know about anodes by now?
They're positive.
They're the positive end of something, right? This, in an X-ray tube, is an anode, okay? It's a disc like that, for lack of wanting to go into the further explanation, we bombard this disc with electrons with an electric charge, okay? And at the point of the disc, those electrons hit the disc, X-rays happen from that, okay? We'll talk about that next class. But we don't have to have this disc spin. It spins for good reasons, good engineering reasons, but the point is right now that the disc has to spin, okay? Something has to make this disc spin, right? I can spin this disc, but I'm not here inside the X-ray tube when it's operating, right? Right? So you've got to have some motor to spin this disc, right? This disc spinning, it's a wheel rotating, right? Just like the wheels on your, your Tesla, right? That spin. I don't know if you guys got a Tesla, but the wheels on your Tesla, right? The wheels on this is the fan inside your house, right? Spinning, right? There's an AC motor that's doing the spinning. AC current can spin the anode disc, okay? Electrons will flow. Let me make sure I get the. In the case of actually making the X, so AC spins this motor. AC operates the motor to spin this disc. But when we actually make X-rays, we'll need the electrons to hop from the negative cathode side of the X-ray device, X-ray tube, over to here. They need to arc. They need to jump across a gap, and they need to slam into this wall. Okay, this anode disc wall. So, in order to make X-rays, we need AC to spin the disc, but we need DC current to run electrons into this positive cathode, or positive anode, okay? We need electrons to make X-rays to only move in one direction. So we're using electricity in different ways. One way is to spin the motor, the other way is to actually generate an electric charge across a small little gap to bombard this disc with electricity. So we need to, in some cases, like actually making X-rays, we need to create DC current before the electricity gets to this point, okay? We need to take and use AC in the machine, but then have certain parts of the machine that operate on DC, okay? So we only get AC from the wall, okay? We don't get DC from the wall. We have to, inside the equipment, have to convert AC current and send it to certain parts of the equipment as DC waveforms, okay? So, let me stop that. What was DC? Direct current, which means what? Only one direction, right? I circle a single direction along the path, though, right? Good. AC current was moving back and forth, oscillating, alternating, right? Okay, so you can take AC and you can make it look like DC, okay? Not perfectly, but you can make it look like DC, okay? That action, that technique is called rectification. So a rectified AC current has no negative pulses, okay? So, this is my last note for today. Let's see how long it takes me to get through this. Okay. Good. We've got a wire here in the middle of the wire. Okay. So a couple of things, okay? Let's start here. So rectification, there's different ways to rectify, and you're gonna have to learn these different ways. In the upcoming lecture, I'll specify these a little bit more in depth, but let me give you 2 ways this can work right now so that you kind of have an idea about it, okay? The first type of rectification, so any rectification is taking an alternating current waveform, converting it into direct current. That's what rectification means. There's different ways to do this, and the different ways are more or less efficient. Let me give you the least efficient way first that makes the most sense though, okay? Remember that alternating current is just saying, move toward positive for some time and then move toward negative for some time and switch that back and forth, right? So in a wire, such as I've drawn very nicely here, in AC, you'll get electrons moving that way through the wire, and then they'll switch direction and move that way through the wire, right? Okay, so if you don't want that to happen, if you don't want them, let's say this side's negative, that side's positive, and you've got your wire, if you don't want that to happen, you can put a device in the wire called a diode. Okay, a diode is a little electrical resistor device that allows electricity, and next time we'll explain how exactly how diodes work inside of them, but the way they work for right now purposes is, electricity is allowed to move one direction, but if it tries to go back the other direction, it's stopped, okay? So in this case, the diode that I've drawn has an arrow pointing that way, okay? Electricity is going to be allowed through, okay? But will not be allowed to go back that way, okay? All of the current trying to go back that way will be stopped at the diode, okay? It won't be able to go the other direction, okay? So with that, you've lost all of your negatively traveling direction, okay? We call this either self or half wave rectification. There it is. Self-rectification. Yeah, here we go. Self or half wave rectification. Okay? And so graphically, it looks like this. You had an AC pulse, and now you don't. The single diode erases the negative pulse. There is no negative pulse anymore. So the advantage is it's easy to do. It takes one single device called a diode, and you only need one of them. The disadvantage is, with AC, you were making power the whole time, right? Now, you have a positive pulse here, right? A gap here, this gap here, and another positive pulse after the gap.
So there's nothing in the gap, right?
Nothing in the gap. How big is that gap in time?
1 inch?
No, not distance, time.
1 second?
Not 1 second. Remember one, yeah, you got it, Abby. One cycle, right? One cycle, well, let me rephrase that. Our equipment operates at 60 hertz, right? 60 cycles per second. There's what I was trying to write. One cycle is 1/60th of a second, right? One pulse of that cycle is 1/120th of a second, okay? You have the pulses, the positive pulses still, that lasts for this distance here, 1/120th of a second, and now you have a gap where the negative pulse used to be, okay? That gap is going to last for 1/120th of a second. That's the gap where the negative pulse used to live, okay? It's gone now. So now you have pulse followed by gap, followed by pulse, followed by gap. There is now an equal amount of pulses and gaps. If you turn this device on, operating at half-wave rectification, you turn it on for 1 second, it's going to be able to deliver as much power as an AC device would be able to, a non-rectified AC device would be able to for a half of a second. Said in another way, you're making half as much power here. Said in another way, half the time you're not doing anything, right? Half of the time you have this device turned on, if you turn it on for 1 second, during that 1 second of operating, it's only actually making power for 0.5 seconds, half of a second, because between every pulse is an equal amount of space of nothingness, okay? So what's better than that, right? Well, let me erase this just a little bit. Actually, you know what? The board is fine. The screen is fine. So what's better than that, okay? So what we can do is use a diode, but use it in a clever way, okay? You use a series, and I'm not going to show it today, we'll show it in next class, but it's a diagram we'll have to look at, but you'll use a series of diodes to trick the electricity to all travel in the same direction. Rather than just canceling out the negative pulses, you trick the negative pulses to go towards the positive direction, okay? And you can do that with a series of 4 diodes, okay? Again, not going to show you that today. I showed you what a diode does. We'll talk more about that next time, about how they exactly operate, and we'll show how the 4 diode system works. But if you can do that, you can have what's called full wave rectification. Okay? This is full wave rectification. All they've done here is taken those negative pulses and flipped them. Okay? Using a series of diodes in the system, we've tricked the electricity to always move in one direction. Okay? Electricity is not that smart, we can outsmart it, and we did. This is called full wave rectification. To be specific, if you've already done all this, which hopefully you have gone through the book, this is called single phase full wave rectification. Okay? I won't talk about phases today, that'll come next time. But yeah, full wave rectification. So this is twice as efficient as half wave rectification. Notice this, you're making something happen the whole time. There is no space where nothing is happening, right? You have a pulse, followed by a pulse, followed by a pulse. You have acceleration, deceleration, acceleration, deceleration, but it's all moving in one direction. So it's effectively like, it's like DC current. Okay? It's like a DC waveform to the equipment. Okay? It would be better if we had this nice blocky DC waveform, but we get what we get, and we have to, the engineers that build this stuff have to make it work with our power that we access at the walls. For today, that's going to be everything I want to get to. In the upcoming stuff, we have to finish this. We have to talk about electromagnetic induction, transformers, AC generators. All right, so I want you guys to sort of start recording here.